All right, so continuing on with equilibrium, let's talk about something called the reaction quotient. The reaction quotient is it's something that's calculated anytime, and you can use this to predict the direction that the reaction is going to go. So same old generic equation, A of A plus B of B equilibrium with C of C plus D of D. The Q is going to be the products over the reactants raised to their powers, the stoichiometric powers, shown there both QC and QP. And Q is at any given time. Remember, Kc, that means that's at equilibrium. So let's talk about some things about the reaction quotient. At equilibrium, the Q equals the K. So those are all values at equilibrium. If Q is less than K, so if Q is too small, that means that Q needs to get bigger. And how does it get bigger? It means that the top number needs to get bigger and the bottom number needs to get smaller. And how does the top number get bigger? It forms more products. So same thing if Q is greater than K. So if Q is too big relative to K, that means that the top number is bigger and the bottom number is too small. So that means the bottom number gets smaller and the top number gets smaller and the bottom number is bigger. That's a shift towards the reactant. That's a shift left. So that's what's going on with the direction of chemical reaction. And if you know the equilibrium constant and you can calculate Q, it'll tell you which way the reaction is going to go. This is valuable information because if you are taking data and you're making something and you want to know when is a good time to stop. If you don't want it to, if you start losing the product that you want, you're like, ooh, I better move the stuff out of my reactor right now. So that's the important thing with this. Or maybe you're trying to get rid of something, like, we haven't gotten rid of it, so let's keep it in there longer. So that's what this kind of stuff does. And if you prefer graphing, so Q or K there, if K is there, that line there, and Q is K is the horizontal line at 1.45, and Q is the reaction quotient. Depending on where the Q is at, it says which way it's going to go. So if the graphing helps you there better, so the y-axis is Q or K, the value of that, and the x-axis is the concentration of the products. Okay, concentration of what? Oh, it has concentration of A on top, concentration of B on the bottom. Okay. So let's use this to predict the direction of a chemical reaction. And we can start here. We have iodine plus chlorine in equilibrium with 2ICl. And the the Kp is 81.9. So reaction mixture contains, has 0.114 atmospheres. So that's a reactant, 114. Cl2 0.102, so Cl2 also a reactant. All over the product, 0.355, and that's squared because there's a 2 in front of that. Which way we'll proceed? So we calculate the Kp. The Kp is going to be 10.8. So we throw it in our calculator. That is 10.8. That's a 10. And Q is less than K. If Q is less than K, that means we need to shift right. So we're going to shift right, and Q is too small, so the top number needs to get bigger and the bottom number needs to get smaller, which means we shift towards products. So shift right. Okay. So let's do, what we're doing next is different examples, trying to get you to start thinking about things in terms of how the equilibrium works and what types of problems you can come across and what you need to calculate. So consider this reaction. 2COF2 in equilibrium with carbon dioxide and carbon tetrafluoride. Kc is 2. In an equilibrium mixture, the concentration of COF2 is 0.255 molar, and the concentration of carbon tetrafluoride is 0.118 molar, what is the equilibrium concentration of carbon dioxide? Okay, so uh, the if you look at this, so our Kc is 2, which equals, it's going to be products over reactants squared, right? And this is a case where we have one equation and one unknown. So we know that the COF2 is this, and the CF4 is that. So we can put in the numbers. 2 is equal to concentration of carbon dioxide. Actually, maybe I'll just go ahead and solve. I like to do the math first. I should stick to what I do in my procedures. This implies a concentration of CO2 is going to be equal to 2 times COF2 squared all over CF4. Now I'm just using algebra, right, to solve for that. And then you just plug in the numbers. So this is 2 times 0.255 squared all over 0.118, just like that. And putting them in your handy dandy calculator, you get 1.10 molar as your answer. So now when you attack these problems, maybe that decimal point, I can move it up a little bit so it looks a little better. So when you attack these problems, you gotta use math logic. In this case here, look for your unknown and then look to see how many unknowns you have and what information is given to you. In this case, your unknown is the concentration of carbon dioxide. And you're given the Kc, you're given equilibrium concentrations of 2 of the species. So the equilibrium expression, writing it out and putting the information you have, then you have one equation and one unknown. You can only, for the number of unknowns, you need the number of independent equations equals the number of unknowns. So that's another math concept. But this is how you do that problem. Okay, now, doing these. All right, consider this reaction. Nitrogen plus oxygen makes 2NO. The Kc is 0.1 at that temperature. Initially, the reaction contains 0.2 molar nitrogen, 0.2 molar oxygen. What is the equilibrium concentrations of the reactants, the products of this mixture? So let's do this. Initially, nitrogen is 0.2, oxygen is 0.2, and inferred, that's 0. So we don't know what happens next. So, well, let's talk about the Q. In terms of the Q, we have no products and reactants. That means our Q is 0. And our Q is 0, which means that we shift right. So if you have a 0 in the product side, you will always go towards the product. If you have a 0 on the reactant side, you'll always go for the reactants. If you have zeros on both sides of the equation, then the reaction is not going to happen. So keep that in mind. So how are we going to change? So we shift right, which means we lose one extent of reaction of nitrogen, we lose one extent of reaction of oxygen, and we gain 2 extents of reaction of nitrogen monoxide. If you want, you can do it this way. You can minus x over 2 minus x over 2 and then plus x. You can do it that way if you want. I prefer not to do it that way. That's my own personal preference. So equilibrium, this is 0.2 minus x, this is 0.2 minus x, and this is just 2x. So then our Kc, so products over reactants, our Kc equals NO squared all over N2O2, right? So what does this equal? This equals 0.1. And from our equations here, we have 2x squared all over 0 0.2 minus x squared. So now we have one equation here. We have one equation, one unknown. And we can solve for it. So let's go ahead and solve for it. How are we going to solve for it? Take the square root of both sides. Square root of 0.1 equals 2x all over 0 0.2 minus x. So with this, though, for those of you, well, if I do the square root, you're like, well, don't I also, so shouldn't this be plus or minus? Well, so this is a problem with math. Okay, so when math is a beautiful model, it is a wonderful thing, but math is not real. Math is not a real thing. What makes math real is the application of it. And if you know what's called the fundamental theorem of algebra, x to the n has n roots. So the fundamental theorem of algebra says that if I have a polynomial raised to some value of n, the number, the n is a whole number. That means that the roots, the time that the solutions for x, or the times that the x-axis, that the equation crosses the x-axis, is the order of the reaction, that n number. So because we squared this, that means mathematically you've created two roots. But in practicality units, in terms of what's real, there's only one real solution. And so mathematically this is plus and minus, but in the real world, in real application, it is not the case. The negative one goes away. This one is easy to see the negative one goes away because you can't have a negative concentration. That one's the obvious answer. Later on, when we start getting the quadratic equation, you have to pick which one is going to be is real or not. So it's not like, and it's not that you create matter and antimatter. Like, I've discovered something new. Like, no, that's just mathematics, and and you didn't create something that's imaginary. That's just a flaw in the mathematical model that we use, or the model that we call math. And only in the application and the understanding of the limitations of mathematics to the real world can you do that. When you apply it to the human brain, or maybe eventually someday AI will be doing this, you have to intellectually figure out which one of these solutions makes sense, and the positive one is the only one that makes sense for this case. Okay, so going back, we simplify the expression. So square root of 0.1 equals 2x over 2 minus x. So let's solve for x. So you have square root of 0.1 times the quantity 0.2 minus x, which is 0.2 square root of 0.1 minus square root of 0.1 times x equals 2x. So now let's add square root of 0.1 to both sides. 0.2 square root of 0.1 equals 2 x minus the square root of, it's plus 0.1 x, and you can draw out the x. X is going to be the quantity 2 plus the square root of 0.1, and then you solve for x. X is equal to 0.2 times the square root of 0.1 all over quantity 2 plus the square root of 0.1, and then you put that into your calculator, and what do you get? You get it to be 0.25. Oh, wait, no, wait, that's wrong. 0.054 molar. Okay. So one of the ways you can check, so that's the answer there, and find the equilibrium concentrations of okay, so we solve for x, and don't forget, what they're asking is for the equilibrium concentration of reactions of the products of this mixture, we have to take this and apply it back up here. So I'm going to change colors in green. This is going to be 0.2 minus 0.054. That is going to equal 0.173. And the same thing with the oxygen. It's going to be 0.173 because of the same thing. And then this is 0.54 times 2. So that's going to be, actually, no, that's 2x. Oh, wait. I did make a mistake. I'm sorry. I was looking at the book. This is actually 0.027. So I was wondering about that math there. This is 0.027. I was wondering about that math. So this is going to be 0.054. So what you're doing is you're applying that x variable then to the solution or to your ice chart. And the initial change equilibrium, and the equilibrium is 0.2 minus x for nitrogen and oxygen, and 2x for nitrogen monoxide. What you can do now is you can do a check. So we know the Kc. Kc is 0.1. We can check this. So is it in fact 0.054 squared all over 0.173 squared? Does this equal that? Well, we throw that in our calculator and we get 0.097. So this tells us that yes, we're very close to 0.1. So because of that, and that's within the 2 sig figs. Within the 2 sig figs, I mean, even then we're you can see there's a 3% error, but you can use this to check to see if you do in fact generate out what you know back. That's a good way to check it. Okay, so let me do a recap on this one. There's a lot of things going on in here. So we have this equation here. Nitrogen plus oxygen makes 2 nitrogen monoxides. And initial change equilibrium. Initially, we have 0.2 molar of nitrogen and oxygen, and we have no nitrogen monoxide. And looking at this, we have no products, so we shift right. So we lose an extended reaction of each of the products because there's a singular coefficient behind that, because there's a 1 there. I mean, you don't list the 1, but it's a stoichiometric ratio of 1. There's 2 for the products. That means you gain 2 extensive reactions. Then you add the lines. So initially, you have the 0.2, so the equilibrium is 0.2 minus the extended reaction for the reactants, and 2 times the extended reaction for the products. And then we have the Kc value is 0.1, and we put it in the equation. Product squared over reactants, so it's 2x squared over 0.2 minus x squared. We take the square root of that, keep the positive root only, and then we solve for the extended reaction, get the extended reaction to be 0.027. Then we plug that into our equilibrium values, and we get 0.173 for nitrogen and oxygen, and 0.054 for the product. And then we, just to be doubly sure, we check our answer, throwing it back in the equation, and we verify that is, in fact, we did it properly. So, a lot of stuff going on there. All right, now let's do a dreaded one. We have to use the quadratic equation. Okay, so consider this reaction here. N2O4 in equilibrium with 2 NO2s. Kc is 0.36. Reaction mixture contains 0.1 molar nitrogen, nitrogen dioxide. What is the equilibrium mixture? So initially, let's see here. Initially, we have 0, and then we have 0.1 there. Okay, so that means we are going to, we're going to shift left because there's a 0 there, so that means we're going to gain x of this, and we're going to lose 2x of that. And that means equilibrium, we have x of this, and we're going to have 0.1 minus 2x of that. And our Kc is going to be products NO2 squared over N2O4, which is 0.36, which is 0.1 minus 2x squared all over x. Okay, so if you remember your rules, the squaring rules, you can use Pascal's triangle. Here's Pascal's triangle. Use the second line for that. It's 1 of each times twice the middle plus the bottom one squared. So you have 0.1 squared, or 0.01, plus 2 times the product. So it's going to be minus 0.4x, and then plus 4x squared. So that's using the if you remember back to your algebra days, that's using those together, and then all over x. So let me multiply x both sides. So let me see. It's going to be 0.36x equals 0.01 minus 0.4x plus 4x squared, and then we subtract 0.36x from both sides, so 0 is equal to 0.01 minus 0.76x plus 4x squared. And let me write this another way. I'll say 4x squared. Actually, I'll bring it over here. So we have 4x squared minus 0.76x plus 0.01 equals 0. So that is, and I've written it above, that is, you can apply then your maybe your favorite equation, the quadratic equation. So that means x equals negative b, so 0.76 plus or minus the square root of b squared, so negative 0.76 squared, minus 4 times a, which is 4, c, which is 0.01, all over 2 times 4. So now you're going to get two answers. So that means, and plug-in is in, and you get x equals 0.176 or x equals 0.014. Now you have to figure out which one of these makes sense. So if you look here, so you have the concentration of nitrogen dioxide there. So it's 0.1 minus 2x. If you do this one here, that means that this 0.1 minus 2x is a negative number. And you're like, I've discovered antimatter, give me my Nobel Prize. No, it doesn't really work that way. That's the erroneous mathematical solution. This is the proper mathematical solution. So we have to use that one there, and then when we apply this, we have our x equals 0.014. And because of that, then we have the equilibrium value is going to be, we want the equilibrium concentrations. So this is going to be 0.014 molar for N2O4, and then 0.1 minus 2x, so 0.1 minus 2 times 0.014, and then this is going to be equal to 0.0272. 0.072. And I'll put molar. And there you have it. And that is your answer. If you want, you can do the check. Check to see if this holds true. So we have 0.072 squared all over 0.014. You put that in your calculator and you get 0.37, and that is close to 0.36. So because of that, we know we've done the thing properly. Okay, so recap with this one. Let's do a recap. We have N2O4 in equilibrium with two NO2s. Kc is 0.36. Initially, we have the product NO2 at 0.1 molar. What are the equilibrium concentrations of both? So with the initial of 0.1 molar of product and 0 of reactant, that means the extent of a reaction goes towards the reactant side, and you have one extent of a reaction for the N2O4, and you lose two extents of reaction for the NO. And then equilibrium value is the extent of reaction for the N2O4, and 0.1 minus 2 times the extent of reaction for the nitrogen monoxide. We write our Kc expression. It's the concentration of the NO2 squared over the concentration of N2O4. We know that equals 0.36. So we plug in the values for our using our ice chart. Then we solve, we FOIL it and we rearrange it, and then using the quadratic equation, we get our extent of reaction is either 0.176 or 0.0014. We have to get rid of the 0.176 solution because it creates an erroneous situation. And then using 0.014 as the extent of reaction, that means we get 0.014 concentration of reactants and 0.072 molar concentration of products in this chemical reaction. And because we're super awesome, we went ahead and checked it, and the check does generate out what we already know. So this is how to solve that one. You're thinking, geez, I hope we don't get to have to use a quadratic equation to solve something. Isn't there something easier? Well, there is. So there is an easier way to solve some of these, and you can use what's called the X is small approximation. So let's go ahead and do it for this one. I'll change colors on this one. So this is just the initial concentration. So let's look at this reaction here. So hydrogen sulfide in equilibrium with two hydrogens and a sulfur. Kc is 1.67 times 10 to the minus 7. So a half liter reaction vessel initially contains 0.012 molar of hydrogen sulfide. So our initial concentration here is going to be 0.025 molar for hydrogen sulfide. And what is equal? So we're given that. What is the equal concentrations of hydrogen and sulfur? So initially not listed, we give it 0. And this is just, so remember, concentration is moles per liter. I'm just kind of glossing over that step. And now, which way does the reaction shift? We have some reactants and no products. We shift right. So we lose 2x here. We gain 2x of hydrogen, and we gain x. X is my extent of reaction to sulfur. So Y2 for the hydrogen sulfide because there's a 2 in front of it. Y2 for the hydrogen because there's a 2 in front of it. Okay, in equilibrium, this is it's 0.025 minus 2x, and x. Now let's do our equilibrium. Our Kc is equal to products, hydrogen squared, sulfur, all over, it's sulfur 2, all over hydrogen sulfide H2S squared, and this equals, actually, this is 2x squared x all over 0.025 minus 2x squared equals 1.67 times 10 to the minus 7. Okay, so now, oh man, you thought the last problem was hard. Look at this. This is a cubic over quadratic. This looks like a horrible mathematical problem to solve. You could do it with a calculator in an instant. This is also, well, if you have a sweet calculator, you know what? Just go ahead and use it. Plug that into your thing and hit solve and be done with it. But I'm going to show you a trick here that we use very frequently in science. And I'll change colors. We call it the x is small approximation. So I've highlighted there in yellow that 2x, the 0.025 minus 2x. What you can do is you can approximate this value. You can ignore that 2x and say this equals about 0.025. So I can apply the x is small approximation. I'm just saying that since the equilibrium is small, right, this 1.67 times 10 to the minus 7, that's a small number. That means we're not going to have a whole bunch of hydrogen and sulfur in this. This is going to be an example of a reaction that does not go very far. So because of that, we can just discount that 2x and say, the 0.025 minus 2x, you know what, that's about 0.025. And now our math becomes much easier. So we're going to have 2x squared times x. This is 4x cubed over 0.025 squared equals 1.67 times 10 to the minus 7. So this is after we applied the x is small approximation. That means x is going to be equal to 0.025 squared times 1.67 times 10 to the minus 7 all over 4 taken to the cubed root. So that's solving for x there, and then you put that in your handy dandy calculator and you get x equals, the calculator, you get 2.97 times 10 to the minus 4. So, okay. And the assumption, though, is you have the assumption that you have 0.025 minus 2 times 2.97 times 10 to the minus 4 is about equal to 0.025. And you know what? It really is. It's within. So this 2.97 times 10 to the minus 4 all over 0.025. This is equal to 0.0119 or 1.19%. So we're really that number only changes by a little over 1%. And depending on, okay, so then question I get with students is when can I apply this x is small approximation when I cannot? Say, well, it really depends on what your error is. Well, the nice thing about this day and age is that we have lots of computers, and if you are programming your computer for your controller and you're a chemical engineer and you've got all these great solver functions, just go ahead and solve it and do an exact thing. Don't have to discount it. Let's say you're doing a test, you're probably gonna be fine for the x is small approximation. Lots of equations use this, actually. So if this is the first time you've heard of the small approximation, it means you're very early in your STEM career. Where else could you like? Let's. I keep on thinking about the Deep Impact probe, the one that NASA sent out, where they took a rocket and they shot another rocket at a comet that was moving. So they used a projectile to hit another moving projectile shot from another moving projectile. Jeez, can you imagine the calculations that you had to do for that thing? Man, that's got to be some calculations, right? I mean, like if I'm weighing myself in the morning, like, do I have to worry about the gravitational pull of the moon if it affects my weight at all? And the answer is no, I don't really care about that. That the error is so small. But if I'm using a rocket to shoot another rocket at a moving uh, comet to try and hit it, do I have to care about the gravitational pull of the moon there? Like, yes, yes, you do. If you're doing something that requires that much of an exact measurement, you really need to be careful what you use and what you don't use. So that's what I mean by managing your error. In this case, managing your error is not that big of a deal. But if you're doing something that requires a super awesome, precise amount of things, you cannot discount things. And I said lots of derivations. A lot of terms are ignored. So when you write things mathematically, this is an example. So this step right there, that is an example of ignoring a term. And you will ignore lots of terms if you go on into, especially engineering, physics and engineering. You will ignore obviously chemistry, lots and lots of terms, especially in engineering. There's terms that are always ignored all over the place, and uh, the famous equation equals mc squared deals with ignoring small amounts here and there. So uh, you'll see these all over the place. Okay, but anyways, let's get back to this. We've solved for x, and we want the equilibrium concentration. Original question is, what's the equilibrium concentration of hydrogen and sulfur? Sulfur, I'll change colors, go back to blue. So sulfur is going to be 2.97 times 10 to the minus 4. And hydrogen is 2x. So hydrogen is 2 times that. So that's going to be 5.94, right, times 10 to the minus 7. So, not 7, 4. So okay, so we've done that. We figured out the equilibrium concentrations of those. Okay, yeah, so recap of this one because I went over a bunch of side stuff. We have hydrogen sulfide, two hydrogen sulfides in equilibrium with 2 hydrogens and 1 sulfur. The equilibrium constant is 1.67 times 10 to the minus 7, which is really small. If we initially have 0.025 molar hydrogen sulfide, how much of the products do we have at equilibrium? So we set up our ice chart, initial change equilibrium. Initially we have 0.025 molar hydrogen sulfide. We have no hydrogen, we have no sulfur. So that means we shift to the right, shift towards products. We lose 2 extent of reaction of hydrogen sulfide. We gain 2 of hydrogen, we gain 1 of sulfur. That means our equilibrium concentration of hydrogen sulfide is 0.025 minus 2 times the extent of reaction. Hydrogens is 2 times the extent of reaction. Sulfur is the extent of reaction. We set up our equilibrium constant as products over reactants raised their coefficients, or hydrogen squared times sulfur divided by hydrogen sulfide squared. So that's 2, I'm going to stop calling extent of reaction, 2x squared times x, all over 0.025 minus 2x. Since the reaction does not proceed very far, we could ignore the 2x on the bottom. So that's the relative to that number. So ignoring the x is small approximation to that number, we can approximate that there, makes our math much easier, and we get our x equals to 2.97 times 10 to the minus 4. And then can calculate back the equilibrium value. The other question I get from students is, why can't I make these numbers close to 0? Why can't I discount those? Like, well, then if you call those 0, you have 0 equals 1.67 times 10 to the minus 7, and that's a logical fallacy. Although that's true that 0 is approximately 1.67 times 10 to the minus 7, but that is still, when it looks to things you can do, if you relate it to that value, that's the value you can discount. Okay. If you're confused, that's okay. A lot of people feel this way about that. Okay, so here is a problem for you to try. If you do the extra small approximation, you can solve it more easily. So why don't you give that a try? Okay, last thing I'll talk about is Le Chatelier's principle. And Le Chatelier's principle, this is something that is actually common sense. It's chemistry common sense. A lot of people don't know this. A lot of people don't understand it, but it makes sense. It works for things outside of chemistry. It works for economics, for instance. And, well, let's talk about Le Chatelier's principle. Le Chatelier and human balance. Le Chatelier's principle, equilibrium shift to counteract a change. So that's what Le Chatelier's principle is. So if I'm standing up and you come up and you push me, if I don't want to push over, I have to resist the force of your push. That is Le Chatelier's principle. I get an external push, and what does my body do? I have to fight back against that push to that my equilibrium will shift to counteract that push, and equilibrium means standing upright. So what's going to happen if my money-wise, say I lose my job, am I going to start spending a lot of money? The answer is no, at least if I was a reasonable human being. If I lost my job, didn't have any income, I would shift my spending habits drastically to counteract that change. Or what would happen if I suddenly got a bunch of money? So if I won the lottery and had $100 million, and now what am I going to do with my spending habits? Am I going to say, you know what, it's time to hunker down and eat more crock pot meals and not go on any trips? Like, oh no, I'm going to be acting like an idiot. I'm going to be buying all sorts of frivolous things with that sudden increase in money, right? So that is Le Chatelier's principle. Okay, but let's go back to chemistry. So reactants and equilibrium products. Reactants are left, products are right. So if the concentration of reactants increases, that means that the system is out of equilibrium and there's too much reactants. The system wants to get rid of reactants. How does the system get rid of reactants? It shifts right to form more products to get rid of the reactants. If the concentration of reactants goes down, that means that more products will react to form more reactants and we will shift left. So same idea of the products. If the products increase in value, the concentration of products, we will shift left to get rid of those products. If the product concentration goes down, more reactants will react to form more products, and we will shift right. And let's talk about other things. If you add a catalyst absolutely does not change the equilibrium whatsoever. There will be no change in the amount of relative reaction of products. It just means the reaction happens faster. If you add heat, so if it's an exothermic reaction means heat is a product. So exothermic heat is a product. That means that the reaction will shift left. If it's endothermic, if you add heat to the reaction. Yeah. So if you add heat to the reaction, endothermic means heat is a reactant. Adding more reactants means you shift right. And the opposite is true. So if you take heat away, if it's exothermic, you're taking away a product, you shift right to form more product. If it's endothermic, you take heat away, you're taking away a reactant, you shift left. And then let's talk about moles of gas. So it depends on which one you have for volume and pressure. So nitrogen and hydrogen makes 2 ammonias. You have 4 moles of gas. On the reactant side, 2 moles of gas. On the product side, that means that the reactant side has more moles of gas. So I like to think of it in pressure. So increasing the pressure means the system has too much pressure. And how does the system respond to it? It responds to it by shifting to the side that has the fewer moles of gas because it's trying to lower the pressure. So it'll shift right. And if the pressure goes down, the system will respond by trying to increase the pressure. It goes to the side that has the more moles of gas. In this case, it's left. And same thing, if you increase the volume, that means the volume, increasing the volume is the same thing as lowering the pressure. So then So because pressure and volume are inversely proportional. The other thing you're going to the system increases the volume, it kind of relaxes, lets its gut out. You're like, I'm just not going to suck this in anymore. I'm going to fill up the area. So that's another way you can look at it. And same thing in decreasing the volume is the same thing as increasing the pressure. You shift right. And decreasing the volume, the system needs to become more compact. So it shifts towards the side of lower moles of gas. Same thing, same logic for more moles of gas on the product side and fewer moles of gas on the reactant side. So the example here, the SO2Cl equilibrium SO2 plus Cl2. If you increase the pressure here, you shift towards the value that has the lower moles of gas, in this case left. Decrease the pressure, you shift towards the side with the higher moles of gas, in this case right. And the same logic for volume. Okay, so that's Le Chatelier's principle. And it's real easy to apply this, and you can tell this right away how a chemical reaction will respond to this. And people do not know this, people don't understand it, and it is so easy, and it'll make you look so smart, and you can apply it to other classes. So other classes like economics. So let's follow this here. So we have hydrogen, 2 hydrogens plus 1 oxygen, equilibrium of 2 waters, and this is an exothermic reaction. What happens when we add hydrogen? Hydrogen is a reactant, we will shift towards product, we'll shift right. What happens if we remove water product? We will shift right towards the products. What happens if we take away heat? We're taking away a product, we will shift right towards the product. What happens if we add a catalyst to this reaction? Absolutely nothing in terms of the equilibrium. What happens if we lower the pressure? If we lower the pressure, that means that we're going to shift to the side that has more moles of gas. In this case, it is the reactant side. Okay, so a lot of talking for me right now. Hope you learned a lot. And you will apply, this is another thing, you will need these skills for the rest of the semester, so don't forget this stuff. If you haven't noticed anything about chemistry, you cannot forget anything. It will always come back to haunt you. So we will be using this for the rest of the semester.